Okay, hello. Do you think we'll get more today? Seems that there's no more people coming. Then let's get started. So, topic for today is ANOVA, which is one of the standard techniques. Basically, if you do your standard statistics course, it's a thing you should learn after a t-test. So it's a pretty basic thing. But despite it being pretty basic and pretty universally used, it's not completely trivial, but there's some tricks to it. And it's, in the end, a very powerful tool in the statistician's toolbox. And I thought I'll explain first the simplest variant of it, called one-way ANOVA, using some simple example, and I do it my usual way of first showing you a bit the idea behind it with some simulations, and then in the end we will find that everything that I explained to you in lengthy R commands can be done by one single R command, which does it all, but of course you will want to know what it actually does behind the scenes. The problem arises whenever you have more than two groups. You remember our typical t-test application was you have a couple of treated samples and a couple of control samples, or you have mice of two different genotypes, and you compare some readout, some measurement, or whatsoever. But what if you have more than two groups? Maybe you have several different treatments. Now, if you have 5 different treatments in one control, one way is, of course, to compare every treatment with one control, so do 5 t-tests, always treatment versus control, and in this way analyze each treatment separately. And that might make a lot of sense, but there's other cases where it doesn't make so much sense, namely if you don't have really one a specific one which is sort of a reference or control condition. And that would be the case if you simply want to see in general whether some outer covariate influence something. Let's say you have a lot of mice which you have found in the field, so we're not part of the problem we have here is that most of the examples that you find in statistics textbooks are from ecology or not from molecular biology. So we are always out in the field now when we talk about this, but you can try to come up with molecular biology examples which would need the same thing. So we go out and we capture different mice with different fur color, and we want to know whether the average weight of a mouse depends on its fur color, whether brown mice are heavier than white mice. And because we have a couple of different categories, black mice, brown mice, white mice, I don't know much about field mice, but let's just come up with this example. We want to see whether there is a difference. And if I now try to compare each group with every other group, I might make a t-test brown versus white, white versus black, black versus brown. That's still 3 tests, that's okay. But if I have 4 or 5 different color groups, then I suddenly have 20 different t-tests, and that doesn't work that well. So let's do it somehow differently, and I now show you how to do that. So I load my tidyverse as usual. And what I've now done, I've looked a bit for an example data set, and I opened some arbitrary statistics textbooks. In that case, where have I actually wrote this? Yes, I actually found the statistics textbook by Quinn and Keogh, Experimental Design and Data Analysis for Biologists. It's a couple of years old, but I think it's still quite useful, especially to find up example data. And they use this example data from this paper, Responses of Diatom Communities to Heavy Metals in Streams, the Influence of Longitudinal Variation. A real typical ecology tip. Now, I'm a physicist. Whenever I read diatom, I think, oh, 2 atoms. You're biologists, you probably know that they are not 2 atoms, but they are some kind of plankton with some silica skeleton. If you don't know them, look them up. They look really nice under the microscope. And they are sort of a basic of your food chain in a sort of marine or watery ecosystem. So obviously we were interested in its species diversity, and we wanted to know how it changes in rivers polluted with heavy metals with not. So I downloaded this data table, which I also found in the statistics textbooks and not in the original publication. And here you see how this looks like. This is the table I found. It has 34 observations from 5 different streams: Eagle Stream, Blue Stream, Snake Stream, Arkan Stream, Chalk Stream. Don't know where the hell they've been, but sounds somewhere like. America. And for each stream, they had a couple of different places, probably upstream and downstream the river, somewhere along the length, and they always measured the zinc concentration. And to keep things simple, they didn't really give a number, but they just binned it into 4 different categories: background level, so nothing detected, low concentration, medium concentration, and high concentration. And then they counted the diversity of diatom species. So they somehow counted how many of the families of a known family or genus or species or whatever of these diatoms they could find, and at which abundance and how diverse this is. And there seems to be some established way in ecology to quantify the diversity of an ecosystem. It's called the Shannon-Wiener Index. It has some beautiful information theoretic context, but I haven't really looked up the details. For all that we are concerned, the more the better. So we assume that if the diversity, if the ecosystem is deteriorated due to heavy metal poisoning, this diversity goes down. So this is the data we get, just these 3 columns. Actually, the data in the paper had way more columns because the title suggests it's not only heavy metals, not only zinc, but also other heavy metals. I've already have to admit I have violated the first rule of statistics in this, namely know the data, know the biology, and all the details about how to do it, which would mean I should have read this paper in detail. I didn't. I only read the one paragraph summary in the textbook, which said what I've just told you. So let's assume that this is true, and if it isn't true, then it's just a made-up example. So if we have such data, the first thing we should always do is to plot the data. So I take my data. It's called medley because that's the first author of this ecology paper. And you can see here I plot simply the zinc column against the diversity column. If you look closely, you will notice that I ignore the stream column. This is bad. I should look at the stream column. The reason why I ignore it because I want to show you one-way ANOVA, which means we only look at one factor. And if you want to look at 2 factors, namely stream and zinc level, this would be 2-way ANOVA, and that will be at the end of the lesson. So for the moment, we pretend that all this data is from the same stream. So if we pretend this, then you see here how it looks like. This is the diversity at background level, at high level, at low level, and at medium level. Up, down looks a bit strange, which is simply because this is not in order. Back, high, low, medium. You see, as usual, R has sorted it alphabetically, which is not what we want. You might remember from previous lessons, there is this re-level command where you can tell for a factor the proper order of the factor levels. If you don't remember what a factor at all is, it's just a number of strings where each string is one of possible values that, I'll turn it around. In statistics, we have continuous and categorical observations. Continuous observations is a number, and categorical observations something like red, green, blue, white, a color or a name or a species or what's that, something which doesn't have a natural order or at least isn't associated with a number. But we still, for internal storage, we have to assess a number the different levels of this factor in order to give it, and now we number them. This makes it a bit a bad example because this thing has a natural ordering, but everything that I'll tell you today applies to things which don't have a natural ordering. So rather than something like these different zinc levels, I would like to have an example with mice of different fur color, because then you can't say white is more than green fur, or, well, green fur is probably bad, but you know what I mean. So I re-level it just to make my plot nicer, but in the end we imagine for the statistics that we now use doesn't depend on there being a natural ordering of our factor level. Still, we can see here a bit what happens. Our diversity seems to go down with increasing concentration of zinc. Each point here is one of sites where they measured zinc concentration in species diversity, and overall it seemed to go down. From background to low, it seems to go up. I don't know whether this has any meaning. Maybe it's a micronutrition. But for our purpose, the statistical question we want to ask, is there any difference between these 4 groups? Or is the diversity completely independent of groups? So this is our null hypothesis, that the diversity of species has nothing to do whatsoever with which zinc group it is in. And this this thing here already suggests this. Now, first, something about how to look at this data. This is how I would suggest how one should look at this kind of data. It's very simple and obvious. We have 31 measurements, so I have 31 points, and I have put 4 different columns to show the different categories I have, and then it just shows the intensity. However, in most papers, you will see this, maybe, a box plot, and in even more papers, you will see this. This is the way how this data is usually presented. As you can see, this is a much better presentation as the one I've shown you before. What's the advantages of this presentation over that? It has several advantages. First, it's impossible to see how many samples we have. So if you only have 2 samples, you can hide this fact. Second, these error bars are somehow sitting in there and you don't know whether they are influenced by outliers or not. So if you have any bad measurements, it's good to hide it. This is the reason why this might be one of the reasons why many biologists prefer to use these box plots, which are completely unheard of in any other science. What I don't understand is why most reviewers don't immediately complain and say, this is unacceptable, show me the data. If I get a paper with a box plot, a bar chart, I usually complain. I say, I don't want the bar chart, I want the data. Then typically comes the answer, yes, but we can't show all the data because it's so much and you wouldn't see all the points. And when you ask, how many points are you talking about? Well, 12. So, we need to get away from these bar charts. For a while, people always advertised these box plots here, where you know the line is the median sample, the lower line and the upper line of the box is the lower and the upper quartile, so that half of all the data is in the box. These lines here, they show you all the way up to the 95% quantile, and these are the outliers which are even further out. This was really a popular way to summarize data, and it was especially useful at the time when people still made plots by hand. Because at that time, you did your statistics anyway, you calculated your median and your quartile, and the box plot like this is easy to draw with a ruler and so on. Most of statistics is about how people did things in the 70s, but I think nowadays this is probably the best way. The only problem here, you don't see the mean and you don't see the error bars, and people are always feeling unhappy about that. So the compromise that you have to come up, if you have an old-fashioned PI, is this here. The other reason you might have an old-fashioned reviewer says, I don't believe a paper which doesn't contain a box plot. So you can put them in gray in the background. Sometimes you also have to put your mean and your standard error of a mean as error bars in the background, but do show the data. Now we have this thing. The next thing we now want to do is to get some statistical p-value on whether this is different or not, whether this is statistically different or not. Here we probably can say by eye this sort of looks different, but is this convincing, and where do we draw the line? So let's do some proper stats. The way how I want to do this now, let's first say what you see often in many papers is pairwise plots. So they show you these kind of things, and then they draw little horizontal lines on top and put little stars on it or little brackets and say there is significant difference between this and that, and between this and that, and between this one and that, but not between this and that. So overall, in order to compare each plot with each other plot, we have to make 6 comparisons, and that's quite a lot. I wrote a little lengthy code here to quickly show you what happens then. So don't get too scared about this stuff. So if I put this here, this is a tibble, and you see I have 2 variables called group and sample. The group is always one of A, B, C, D, and value is just a random number. So group is one of 30 values simply taken from A, B, C, D, and value is just a random, a normal random variable with mean 10 and standard deviation 3. And what I will now do is I do all these pairwise tests. To do all the 6 pairwise tests, if some of you want to learn a bit of R, you can try to understand what's going on in this lengthy thing. You can very quickly go through it. Where is this? X. Sim data not found. Here I write it in sync data. Here you see this expand command. It somehow now calculates all the groups, A versus A versus B, A versus C. when I now filter them, that I only get the 6 comparisons that I actually have. And now I do a t-test where I always compare group A versus group B for this simulated data. Remember, this was my simulated data with no change whatsoever, and here I do my my p-value, and in the end I add a little star to show you whether it's significant. So let's do this a couple of times. Relays it. Yeah, works fine. It was random data, nothing significant. Do it again. Still nothing significant. This actually works surprisingly well. Usually there is always, because if you do 6 comparisons, now we have 2 significant changes. Now it probably should come up. Another true one. So usually I would expect that in about half of the cases I would find at least one true value, because 5% is the probability to get a p-value below 0.05, and for this to happen in one of these 6 ones is quite likely. So whenever you see this kind of multi-comparison, you have to be alarmed, because it's simply not proper to check with a significance level of 0.05 20 different possibilities. Maybe this differs with that or this with that, and it doesn't work. So how can we do this better? And the standard way to do this is to use one-way ANOVA. As I told you, there is a single R command here. You remember this is my medley table, and it has here the zinc concentration and the diversity. We're ignoring stream for now, and we want to know whether diversity has any dependence on zinc. And now we ask ANOVA, and it tells us p-value of yes, this is significant. So this is
just a question. Do I understand properly before? So would it be a proper, even though not the best way to do it with t-tests, if I divide the p-value by the factor of 6?
Yes, this is called the Bonferroni correction, and you can do this. You can probably even argue that it's sufficient to divide by 5, because these are not all independent things, but it's somehow clumsy and hard to understand. So here ANOVA it looks very simple. You just tell what you want to compare with what, and here's the data table, and you say give me an analysis of variance, or ANOVA, and it tells you the analysis of variance said that the mean squared variance goes down from 0.8 to 0.2, and that is significant. So what does this mean? Let's first here make a little plot, which I showed here. To the right, you've already seen this plot. With my measurements, and this time I added a bit of jitter so that they don't sit all on the same line, so it's easier to see. And on the left, I simply put all of them on the same axis. So these are simply the same dots as here, but all pushed together in one thing. Now, one way you can look at this is that you say the overall variance of all of these points here. So if I simply take the variance of the whole columns is 0.27. If I take the square root of this is 0.5, so I have a standard deviation of 0.5 here. If I look at these individual ones, each of these individual ones seems to have a smaller variance. You see, each of these ones is tighter. If there were no connection between this group and that one, if each of the group would just pick out a random sum of them, we would expect that the variance is probably nearly the same. So, but here we now have a point that the variance is, I quickly show you this again, that the variance of these ones is a bit smaller. And we can now think about, is it sufficiently smaller? So let's first calculate the variances. Here, this is the variance of a total thing. It's now helpful to remember how a variance is calculated. Variance means you take the average, you calculate the mean, and when you look for each data point, you ask how much does it deviate from the mean. And these deviations from the mean, we square them. So the variance is the average squared difference to the mean. I show this again here. This here is, these are all my data here. This is the mean of all of them, 1.69. This is what I get if I subtract the mean. Some of them are above the mean, some are below the mean. Now I square them. Now I get these values. And now what I next might do is I add them all up, all these squares. get 9.08, and now you might remember from the formula that you're now supposed to divide by the number of samples, so that it's something like an average of the squared deviation. But for reasons that I won't go into again now, we don't divide by the exact number, but by the number minus 1. And then we get 0.27, which is what we got here as variance. So this is how we calculate a variance. What I want to focus on now is the numerator, this sum of squares. We simply call it SSQ for sum of squares. And the sum of squares is something which is useful, because I can calculate the sum of these. Here I have written again how I calculate the sum of squares, this time in tidyverse notation. I say here diversity minus mean diversity squared and the sum. And now I do this again, and this time I put here a group by zinc. You remember group by means that the next summarize should done for each group separately. Now I get here, I have now essentially taken all these squares here, and I changed two things. First, I didn't simply add them all up, but I added the 4 groups separately up. And second, I don't subtract the overall mean, but I subtract the mean of the individual groups. The fact that we subtract the mean of the individual group now has the effect that the sum of all the squares will be lower, because the values can be closer to the group mean than to the overall mean. Because the overall mean has one size fits it all, and the group means will be slower. So this is what we do here. The overall mean, if we take the overall mean and sum them up, we get 9. But if we take the individual means and sum now these numbers up, we don't get 9, we only get 6. So that's what I do here. I take the group, I calculate the means for each group, and then I sum them up. And now we have a reduction of the overall sum of squares from 9 to 6. And this is now the question whether this is significant. If this is significant, we say the ANOVA tells us that there is an influence of the group on the outcome, otherwise it isn't. And in order to find out whether this is significant, we can now do a little simulation. So, what do? I go back to the simulated data that I've just simulated with 4 groups and just random values. You remember that in that case, there shouldn't be a random effect, but there might be, but only a slight one. So I again calculate the total sum of squares, and if you look it up in statistics textbooks, there's a whole jargon of terminology, and this thing is called TSS, simply for total sum of squares. And then after we take the group means, we call what's left the residual sum of squares. So this is the residual sum of squares. You see it went down from 151 to 146, much less than before. We went down from 9 to 6. This was going down to 2/3. Now we only went down a little bit. So one way to see this is to say from this total variance, which is associated with this sum of square, we could explain a little part by this group, but most of the stuff stays unexplained. So this is how people like to talk about explained variance. They say we have this overall variance, and if we knew all the things which cause this variance, then we can explain them all. And here the zinc level explains a little bit, but maybe if we now had other categories like which stream it is or how much the copper concentration is, the individual groups would have even lower variance, and so every factor explains more variance. Of course, it might only seem to explain it, but maybe it really explains it. So we have this terminology that we say the total sum of squares is we have a total sum of squares, we have what's left over, the residual sum of square, and the difference between the two we call the explained sum of square, and say this is explained by it. And in this logic, I can now say that here from my total of 9, I have a residual of 6, so about 1/3 is explained and 2/3 stay unexplained. In my simulated data, it looks much different. If I now calculate how much is unexplained, it's 146 over 151. This is about 98% is unexplained, and only 2% is explained in quotation marks. So how can we see what's typical here? I do my favorite thing, doing a lot of replicated simulations. So look at it again. I calculate a random table here with randomly assigned letters A to D and randomly chosen values which have nothing to do with each other, store it in my variable sim data. When I use my simulated data, calculate the total sum of squares here, store it in the variable TSS. When again I use my simulated, calculate for each of the groups A, B, C, D separately, get a slightly lower number which I call the residual sum of squares. Now I divide the two by each other and say 75% are residual and 25% seem to be explained. I call this the unexplained fraction of the squares. And now I say let's redo this simulation always with freshly random data, 3,000 times. And this now runs a bit. I think it runs about 15-20 seconds. Now I can look at the histogram of it. And up, what is this? And here you see the histogram. Typically, we randomly, it seems that we can explain about 80 to 100, that about 80 to 100% stay unexplained. And a change from 1 to 10% seem to be explained. So this is now the way how we have to look at that. If we have 30 samples and we have 4 groups, then we should explain so much of the variance should be expected to be explained by chance. And if we see things to go down much less than that, we can say this is significant. So, but as usually, there's a lot of history. This whole concept that I'm currently outlining is from the 1930s. Back then, there weren't computers, so you had to think about how to rationalize and optimize your computation and how to best make it as little work as possible if you have to calculate everything with a mechanical calculator. So people came up with a certain way to arrange it, and we are still stuck with it. So one thing is that we have something which is called the F statistic, and the F statistic is given by this formula here. So if we are here at 0.8, for example, then we would say we have 20% explained and 80% unexplained. So our F statistic is 20 to 80. So we divide the explained fraction by the unexplained fraction, and then we multiply by what's called the degrees of freedom. The degrees of freedom are these things at the denominator of the statistic. So we multiply by the number of samples minus the number of conditions. We had 30 samples and 4 groups. 30 minus 4 is 26. And this here is the number of groups minus 1. That's 3. That's what you always have here. Now we don't really need to understand why we exactly take these and minus 1. And this is an interesting story, but maybe it doesn't fit into 1 hour. So I just do it now. So for now, this is just basically the same information as before, now slightly rescaled. You can imagine I can calculate my unexplained fraction from the F stat and backwards. I can just invert this formula. So if I do this, then I get here now my histogram of the F statistic. This is the same histogram as before, but now just rephrased in this, not the fraction unexplained, but the ratio of explained over unexplained, and then multiplied by 26/3. The reason why this is interesting is because here is just the histogram, and what you can now do is there is something called the F distribution, which has a well-known formula. And if here it is, the formula for the F distribution looks a bit annoying, but it's not very difficult, just something to the power of whatever. And if in order to calculate this formula, you want 2 things. You want X, this is your F value. You want to know D1 and D2, these are these odd numbers, 26 and 3. That's the reason. If you do the math and think about it, you realize that you have to look at this here, the number of groups minus the number of samples, and put it here as D1, and the number of groups minus 1 and put it here, and then you have to calculate this formula. And when you do that, you get for each F value a corresponding probability. And this probability is now what we've simulated here. It's actually the probability that just by chance we would get this value. Here you see my the F statistic which I've computed according to this formula. So dF is just a way to, it's just a shorthand for this formula in R, very short shorthand because you need it often, gives you exactly the theoretical expectation. So if I now do an ANOVA and I get my F value according to this logic, residual sum of squares over total sum of squares, and then fraction explained over unexplained times these 2 degrees of freedom, when you get your F value. And now you just have to look up in a table which tabulates this purple value and find out your corresponding P value. In practice, this now looks like this. For our let's calculate here for our medley stuff with values in our true data. So in our zinc data, we have here this TSS, this RSS, this unexplained fraction, and here we have the TSS minus RSS, so the explained fraction divided by the unexplained factors times the degrees of freedom, 30/3, same strange formula as before. And as you see, we get 3.93, and again I can take this 3.93, put it into my F statistic formula, say 3 and 30 degrees of freedom, and then it gives me this p-value, 0.016. And this is what the ANOVA table has given us before. So this is what ANOVA does. It imagines that all your data is just random and asks how much would the sum of squares go down if you would just take the mean values of the random ones, and how likely is it that the observed reduction in sum of squares is compatible with that. So quickly let's go back to where we started here with this plot here. This was our thing. We see here the scatter of all the data, and now we see that the scatter in each individual group seems to be lower just because we sorted it into groups. And it could now be that this reduction in scatter is by chance, or it could be that this reduction is because actually the random scatter in our data is lower than it seems here, and the extra scatter is just because the mean values are different. So now we can say that the mean values are really different, and that our real model is that each zinc concentration is associated with a certain mean value around this, the stuff scatters with this value, and the fact that this the scatter here looks larger is because we threw together different mean values. So we have now shown with a significance level of 0.017 that these things here fit together like that. Another way to look at it, to do something, is of course to do a permutation test, which we've always now done as an alternative. My permutation test works as this. I start off as before and calculate the total sum of squares. We already know that one. It's still 9, I think. Yes, it's still 9. Now I calculate the residual sum of squares. Also still the same as before, 6. And now what I now do is that I redo this calculation of the residual sum of squares. Here, this is the same code as up here, except for one extra line, that one here. You see, I have put here a sample zinc, so I just shuffle the zinc column, and if I shuffle the zinc column, I destroy the association between the zinc measurement and the values. And if I destroy this, then the reduction in sum of squares will now only be due to chance. And we can see what kind of RSS values would we get in that case. So here I do this once. Remember, 6 is the RSS value we got with the true values, and if I do it with shuffled values, I get 8, 8.7, 8.9, 8.4, 8.12. So just coming up with arbitrary assignments to values reduces RSS by a little, from 9 to something like 8 point something, but it doesn't go all the way down to 6. Again, I use my replicate command to do this 1,000 times. And if I do this 1,000 times, I can now make my histogram of all these permuted things. And in this histogram, I now will put 2 lines. So the histogram, you remember, are the RSS values. So the sum of squares after assigning the fake shuffled permutations and the purple line is the total sum of squares. And you see with a random assignment, total sum of squares goes down only a little bit from 9 to maybe 8, at the very best to 7. But the one which we observe with our real data is the green value. These are the 6 points which we get with a proper assignment. And now I can ask, how often did our random permuted value are below this? So I can take here, sum up these values which are below the green value and compare them with them above the green value. So how many are below the green value? 12. And how many are above the green value? 988. This gives me a p-value. The probability that this happens out by chance seems to be roughly 12 in 1,000. So to get a p-value, I decide 12 divided by 1,000 is 0.00012. I only do one extra care. I add here +1 on the numerator and the denominator, so I don't do 12 by 1,000, but I do 13 by 1,001. I do this because imagine we would find nothing here to the left. This might be simply because we haven't done enough permutations, but we would conclude that the p-value is 0. And it can't be. If we do only 1,000 permutations, we shouldn't cite a p-value which is lower than 1/1,000, because we couldn't know that. And this is why the rule is, if you cite permutation p-values, you always add +1. So you see our permutation test has given us a p-value of 0.013. Our ANOVA test has given us a p-value of 0.018. That's really sufficiently similar that we can say that these two tests more or less give us the same result. The reason why they are not exactly the same is, of course, in the p-value we used random permutations, and in the F ANOVA we used a specific formula, this F formula. Second, the F values, they have been done under the assumption of normally distributed residuals. So you remember in my simulation I distributed normal values and assigned random groups. Now what if our data is not normal? If our data is not normal, things might deviate a little bit. And there was a long argument in the history of statistics about how bad this is. And up to the 80s or so, people always cautioned, if your data is not normal, you can't do ANOVA. Later people did a lot of calculations and simulations when they had sufficiently powerful computers to simply say, let's try lots of different non-normal things, came to the conclusion. Actually, in most cases, if your data is not normal, ANOVA gives you too high p-values, so you err on the conservative side. That's also what happened here. Probably 0.12 was the correct result, and 0.017 is a little bit too pessimistic. But still, now that we have fast computers, we could always do permutation tests. They are safer, they don't rely on any assumptions, so I personally prefer them. However, they have a couple of disadvantages. One is, of course, they are less standard. We had to write a bit of R code to do the permutation test, while the ANOVA is just done with this one standard thing. And if you write in your methods, we just used ANOVA, everybody knows what you mean. The second advantage, but the more important ANOVA, is that there's a lot of cases where we can't do permutations. Here we can do permutation because we have a simple one-way design. To each measurement value we assign one factor level, namely the zinc concentration. And that's what we get here. But sometimes we assign more than one thing. For example, zinc concentration and what stream it is. And then it gets difficult to permute. Because how do I permute two things at the same time and still get a good reconstruction? Sometimes I can permute, sometimes I cannot. There's cases where it simply doesn't work. Okay, before I come to two-way ANOVA, let's stop here for a moment and think about what we've learned, what we now may actually conclude. An important point you always have to think about when you do these kinds of analysis is confounders. What's a confounder? Everybody knows what a confounder is. It's probably the most important word you have to think about in this case. Given all this, what would you now say? Can we now conclude really, from just what we've seen, that the zinc concentration in a river influences the species diversity? Who thinks yes? Okay, I shouldn't ask this because, of course, everybody knows that I now come with a counter argument. There's a couple of caveats we have to think about carefully. One thing is, of course, a p-value of 0.017 isn't that great. I've argued already earlier that 0.05 is a way too lenient threshold, in my opinion. So 0.017 should be, yeah, it's probably good enough to write a paper, but not to put this into stone. The more important thing, however, is already hinted to in the title of the paper. And as I've said, I haven't read the paper, but the paper title said that they have measured the influence of heavy metals, plural, heavy metals. So they probably also measured other stuff. And I imagine that they are correlated. Because if you have any kind of source which leaks heavy metal, be it a natural deposit or be it a factory or a mining facility or whatsoever, they typically will release several heavy metals. And if you have high zinc concentration, you might also have high copper concentration, say. So there might be some other heavy metal with which our zinc concentration is correlated. And this, of course, means that we don't know whether it's really the zinc which causes our diversity to drop down. Anything else which is correlated with the zinc could also be the real cause. And it could be that zinc is only an intermediate, a proxy measure for the real cause of it, and the real cause is correlated with zinc. There is no way to ever distinguish these two things. But and so this is not a statistical question, but it's more a biological question. You have to think about, first you have to ask what else is a likely cause, and you have to measure them too. If afterwards you now were to find that zinc is significantly associated with diversity loss, and copper too, when you cannot write a paper, zinc and copper are both bad, because if zinc and copper are highly correlated, you would say one of the two is bad, or maybe a third one that we forgot to measure. So in principle, we can never say this as easily. That's a bit of where this whole correlation doesn't mean causation come from. But we can say with some certainty that there is some connection between zinc and outcome, but we don't know whether this connection is causal or whether maybe zinc is just a proxy which is correlated to something else. And we call this confounders. If we measure things and we notice that two predictors are both correlated with each other, when we say they confound each other. So, and by they confound each other, we mean that if one is the cause, the other will also appear to be a cause, and we can't know which of the two. And hence, if you design an experiment, a very important thing is to think beforehand about potential confounders and check these confounders and make sure that you measure them. Now, there's two kinds of confounders. There might be biological confounders, like here another heavy metal, but there might be another confounder which might be something completely unexpected and technical. Maybe I have more measurements from sites in industrial area where the concentration is higher, or I use different technical equipment. And so whenever your outcome, your value of interest is correlated to anything, any technical aspect of your measurement, you really get into trouble, because then you might get into these. For example, batches might be confounding. Let's say they have done beforehand following example, let's say these people have decided to make their measurement campaign. First, at some point they decide to go to all the downstream places because they are easily reachable, they're at the coast. And then a year later they decide, okay, now let's travel to the remote sources where the things start. And of course there the water is cleaner. Typically, clean water is in areas which are remote and hard to access, while dirty water is in industrial urban areas. So if you're now lazy and decide, let's first drive to all the urban areas, and next year we'll drive to the clean areas because they're harder to get there, and first we have to apply for travel money, then you suddenly have a confounding between your zinc concentration and the time when you took your experiment. And maybe a lot have changed since then because it's a different season. And this is the kind of confounding which is really bad, because when your problem is not that you have identified the wrong heavy metal, but you had identified an effect which actually was just an artifact from the way how you have organized your measurement campaign. So that part is of course also especially important in molecular biology, and it's the reason why you never should do all your controls on one day and all your treated samples on another day. But if you need to do several days, do one control, one treatment on one day, the other control, the other treatment on the other day. Otherwise you have a confounding between treatment and the day when you did your experiment, and everybody knows how much can change from one day to the next in a lab. And of course, if you read a paper, you will never know because they won't tell you about this kind of confounding. Now we actually still have 10 minutes, so I can quickly show you the gist of two-way ANOVA. And to do this, remember I have ignored stream so far. I shouldn't do this because it would have been so easy. Here is the plot we did last time, and now I just added here the value color equals stream. And now we get here these things. The other thing that I've added, if you ever do it yourself, I used another color palette which makes it a bit easier to distinguish these things. And what you can see now is there is indeed quite some difference between the streams. The chalk stream, for example, always tends to be higher in diversity than what's the orange one, than the splat stream. This makes a lot of sense that the species diversity will differ from stream to stream, because I don't know much about the ecology of diatoms, but I imagine that a little piece of silica shell can swim, so they will swim down together with the current of the river. So it will depend a lot on the ecosystem at the source and how much comes in there. Which, by the way, is another confounder. Maybe we lose them while they swim towards the end, and we should also make sure that the position in the river, upstream versus downstream, isn't a confounder with our zinc concentration. I hope we've done this in the paper, but as I said, I haven't read it. But here you now can see this, and now we can, of course, wonder maybe if we now may calculated our mean not only separately for each of the four zinc concentration, but also separately for each stream, we would get higher we would explain even more of the variance. Of course, you can imagine the mean that we should put for the chalk river should always be a bit higher than the mean that we should put for the splat river. So one way is to look at all the combinations of the 6 streams times the 4 combinations, which is 24 combinations, but that's not so good because if you calculate 24 means and we have only 30 samples, there's hardly anything left. This is the reason why we called this degrees of freedom. You remember I said earlier the number of samples minus the number of means that you calculated is called the degree of freedom of the experiment, the residual degree of freedom. And as you can see, if the number of means you calculate is equal to the number of samples, you have left 0 degrees of freedom, which is akin to you have no freedom to conclude anything from your measurement. So the way how we do it instead is that we calculate one mean over all for each stream, averaging over all the things, and one mean for each. Not quite like this. What we will do, maybe I show you quickly what this linear model does if we calculate this here. You see this linear model, this is the inner part here, it's called linear model, and now you can also see what I have here. Diversity is stream plus zinc, and what it has calculated is something called here coefficient. It has an intercept coefficient, which is the value that it will associate with the first stream, arcan, at background zinc concentration. So whenever it has a sample which is background zinc concentration, it will assume the mean 1.87 and subtract this from the sample. So all these, and do we have any arcan? Well, we don't have any, but if we had any, we would subtract that one to get our square for our sum of squares. Then if it is not arcan stream but one of the others, we always add these values. So when it is a blue stream or chalk stream or eagle stream, we add 0.11 or 0.44 or 0.20 to this intercept. And the same way, if it's not background, but if it's low, medium or high concentration, then we add these values to it. And that way, and we'll have to go maybe a bit more detail next way, but you can imagine we sort of assume, we sort of get these coefficients, and R has tried to find these coefficients to get the minimum sum of square. So the idea is that for each combination of the two factors, we get an expected value or a fitted value, how we call it. Beforehand, in our one-way ANOVA, the way it works is that we said the fitted value is simply the mean of a group. And our sum of square was the deviation from this mean squared and all summed up. Now the sum of square is the deviation from the fitted value, and because we have two factors, the fitted value is now not simply the mean of a group, but instead we try to find for each possible combination one way by making this formula saying the fitted value should be an overall value, sort of a base level of diversity, plus an effect in case it's a specific stream, plus an effect in case it's a specific zinc thing. So we add 1, 2 or 3 numbers, and then we get the fitted value for this. So if I take, for example, this purple one, this is not chalk, this here, which is low and splat, I would say the expected value for that one should be 1.87 plus minus 0.56 because it's splat, plus 0.11 because it's low in zinc. And then we get a value which is probably 1 whatever, and that value sits, and that value might sit a little bit next to it. And when we see how much this deviates, and take this as a deviation, square it and sum it up, and then we get a certain sum of square. And if we change these values, we get different sum of squares. And what R has now done is it tried to find the specific values here which give the lowest possible sum of squares. In our one-way ANOVA, R did exactly the same, only it turns out if you want to minimize the sum of squares, simply have and all you're using is one value per group, then the value which you should give is the mean. Because if you use another value as mean, the sum of square would always go up. And this is the starting idea of the whole of ANOVA, this observation that the mean is the specific value, if we define a sum of square as always the squared deviation from some fitted value, when the mean is the fitted value that we should take to get the lowest sum of squares. And now here we try to find fitted values which generalize this and sort of find one fitted value for each combination by adding up these so-called coefficients and try to find the minimum. And then we can now ask how much does this and then we can compare this case now with a one-way ANOVA case where we only use diversity versus stream. So we once use only the stream things, or we use only the zinc things, or we use nothing at all in order to see whether our sum of squares goes significantly down if we add extra stuff. And that's what this ANOVA table here does. If I now execute a full command with the ANOVA around, it makes us this table, which tells us that the sum of squares over everything is 9 as before. And these 9 are now partitioned. If you just make an ANOVA which only accounts for zinc as we've done before, the sum of square goes down by 4, and when we are going down from 9 point something to the 6 point something which we had before. So this 4, this is simply the difference of a 9 and the 6 which we had before. If we do the same only accounting the stream, it goes down from 9 to 7 point something. And if we do it for both, so if we just use the coefficients I've just shown, we're down at 3. And now you can ask for each of them how important it is to get down. Stream is marginally significant. There's some difference between the streams, but not much, because it reduces the sum of square by 1.8. But zinc now reduces the sum of square not by 3, but even by 4. might not sound much, but look at this here. Reduction by 3 was here. Reduction by 4 is here. This really makes the p-value very low. So once we have accounted for stream, so we have already removed the effect of stream, the effect of zinc becomes much more pronounced. Another way how you can look at this is, and this requires a bit of math to show that these two things are the same, is that you regress outstream. That means that for each stream you calculate the average of a stream and subtract this average from the values, and then you have removed the effect of stream, and then you can do one-way ANOVA. The difficulty here is when I say I subtract the value, the mean for each river, I have to be careful about how I do this subtraction. Can I simply take the mean over all of them? And I can only do this if it's balanced. That means I have for each zinc concentration for each river the same amount, but that's not true. For some rivers we have more high values, and for some rivers we have more lower, and so in the end you have to do this. But conceptually, what we are doing here is that we are removing the effect of stream, and the effect of stream of course causes variation, and once we've taken out this variation, the effect of zinc becomes valuable more crisp. So here you see that that accounting for the differences in stream has much increased or significant. Now we have a p-value of 0.0001, which sounds much more convincing and shows us that there really must be a connection between zinc and either zinc and diversity, or between something which is correlated with zinc and diversity. So the last part, the two-way ANOVA, now was a bit sketchy, but I thought I might do it the way that I first show you at length the one-way ANOVA and quickly present how two-way ANOVA works, and maybe I can come up with a more plastic way or some nice visualization to do it next time. But for now you roughly see where this is going. One-way ANOVA is in a way easy to understand. If you remember, that is this idea of taking the group means and seeing how this reduces the variance. If you take for each group the group's individual mean instead of the overall mean. But once you have more than one factor, you need this multi-way ANOVA thing, which allows you to account for all of them. And in the way how you do it practically, it's really no more difficult. You just have to add here an extra, all your extra columns. Only have to make sure that you measure all the columns, and you see here how important it can be to measure the right columns. Of course, for them it was easy to measure which stream they were at. They just had to look at the map. If you're doing a lab experience, it might be the same thing. That obviously this could now be you have the effect of a treatment on some phenotypic readout, and your second column might be which strain or which genotype it was. And obviously you want to try different strains or genotypes. And if you now remember the RNA-seq example of last time, where we had this airway epithelial data, this was exactly such a case. They looked at the effect of dexamethasone on gene expression, and they had an extra variable which they wanted to account for. One of the so-called blocking factors, like here stream, which sorts everything in different blocks. In that case, it was the 4 different cell lines that they used, because they had 4 cell lines derived from four different donors. And in the DEC call, we also gave a formula, and it had the same thing. It's a tilde cell line plus treatment, the same way how it says here tilde stream plus zinc, and it was exactly the same logic. So what we've done last time was a two-way ANOVA for each gene separately, and this is also the reason why I have to explain to you ANOVA now. One, because it's really a workhorse for a lot of single variable thing, and second, because it appears also whenever you do high throughput stuff. So we can sort of bring these two things together. And actually, if any of you can think of a lab experiment where you have this kind of data table with 2 different columns, where one is what you're interested in and one is what you vary, and one is something which is your blocking factor, which you also need to account for, it might be interesting to discuss an actual wet lab experiment rather than some ecological field studies. So tell me, and then we can use this example for the next time. So questions about this? Otherwise, mill it in your head. I upload this RMD file, then you can read through it, see whether it makes more sense on second reading, and see you not next week, I'm skiing, but in 2 weeks for whatever we do. Okay, thanks.